Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the key value store, the foundational building block behind almost every distributed system, from Redis and DynamoDB to the storage engines inside Twitter, Snapchat, and LinkedIn. We'll cover how to design a store that serves billions of reads and writes with single-digit millisecond latency, handles node failures, scales horizontally, and keeps data consistent across regions. Whether you're preparing for a senior engineering interview or building distributed storage at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the key value store, the foundational building block behind almost every distributed system, from Redis and DynamoDB to the storage engines inside Twitter, Snapchat, and LinkedIn. If you have ever wondered how to design a database that serves billions of reads and writes with single-digit millisecond latency, handles node failures gracefully, scales horizontally, and keeps data consistent across regions, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building distributed storage, let's get into it. Here is the core problem. Modern applications need to store and retrieve massive amounts of simple data, such as user sessions, product catalog metadata, feature flags, rate limit counters, shopping carts, and leaderboards. They need extremely fast lookups, usually by a primary key with predictable latency. A traditional relational database is too heavy for this. It enforces schemas, supports complex joins, and struggles to scale horizontally when write throughput explodes. But building a custom key value store introduces its own challenges. How do you distribute data across thousands of nodes so that adding a machine does not require reshuffling everything? How do you keep replicas in sync when networks partition and nodes crash? How do you guarantee that a read returns the latest write without sacrificing availability? How do you handle hotkeys, large values, and cross-region replication? These questions are exactly why key value stores are one of the most interview-worthy topics in system design. Let's walk through the functional requirements. First, the system must support basic operations. Get, put, and delete, where every item is identified by a unique key and stored as an opaque value. Second, it should support range queries or ordered iteration when needed, because some key value stores expose sorted keys, which enable prefix scans and secondary index patterns. Third, it must support atomic compare and swap or conditional writes, so clients can update a value only if it has not changed since the last read. Fourth, it must support time to live, allowing keys to expire automatically, which is critical for sessions, caches, and transient data. Fifth, it must support configurable consistency levels per operation, so a client can choose strong consistency when correctness matters and eventual consistency when latency matters. Sixth, it should expose batch reads and writes, administrative commands for cluster topology, and replication or backup configuration. These capabilities make the store usable for a wide variety of workloads. Now the non-functional requirements. Low latency is paramount. The P99 read and write latency should be in the single-digit millisecond range, and even lower when served from memory. High throughput is equally important, because a back-end store can receive millions of requests per second. The system must scale horizontally. Adding nodes should increase both storage capacity and request throughput, ideally linearly. Availability is non-negotiable. The store should tolerate node failures, rack failures, and even data center failures without going down. Durability matters. Once a write is acknowledged, it should survive a configurable number of concurrent failures. Consistency requirements vary by use case, so the system should offer tunable consistency from strong to eventual. The system must be operationally simple, supporting automatic failover, rebalancing, backup, and restore. And finally, it must be cost-efficient, balancing memory, disk, network, and CPU resources. Here is the high-level system architecture. The client SDK or application sends requests to a load balancer, which forwards them to a coordinator node. The coordinator uses a consistent hashing ring to map each key to the nodes responsible for that key, typically the first n successors in the ring. For writes, the coordinator routes the request to the primary replica and waits for acknowledgments from a configurable number of secondary replicas. For reads, it routes to one or more replicas based on the requested consistency level. Each storage node runs a local storage engine, such as a log-structured merge tree, a B tree, or a hash table, backed by memory, SSD, or disk. A replication manager keeps replicas in sync using a protocol like primary backup replication or consensus. A failure detector and gossip protocol propagate membership changes and topology updates. A metadata service stores the ring assignment, partition map, and configuration. An optional cache layer absorbs hot reads. Background jobs handle compaction, repair, snapshots, and cross-region replication. The key metrics to memorize cold. Latency distribution P50, P99, and P999 for both reads and writes. Throughput, measured in operations per second or bytes per second, split by operation type. Cache hit rate, the fraction of reads served from memory without hitting disk. Replication lag, the time between a write on the primary and its reflection on the secondary. Node recovery time, how long it takes to rebalance data after a node joins or leaves. Quorum success rate, the percentage of operations that meet the required read and write replica counts. Data durability, the probability of data loss under a given failure scenario. Conflict or repair rate, the number of read repair or anti-entropy operations needed. And operational cost, the CPU, memory, disk, and network consumed per request. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. A mobile application wants to store user session data for a popular e-commerce site. During login, the app calls put with the session key, user identifier, and a 30-minute time to live. The coordinator hashes the key, maps it to a partition, and writes to the primary in two replicas using a write quorum of 2. Later, when the user adds an item to the cart, the app calls get with the session key. The coordinator reads from one replica with a read quorum of 1 because eventual consistency is acceptable for this operation. The response returns in under a millisecond. When the user checks out, the app calls get with a strong consistency level, so the coordinator reads from 2 replicas and resolves any mismatch. The time to live expires after 30 minutes, and the background expiry job cleans up the key. When a storage node fails during a holiday sale, the system automatically promotes a replica and reroutes traffic, with no manual intervention and only a brief latency spike. The core models and algorithms. Consistent hashing maps keys to a ring and assigns virtual nodes to physical machines, so adding or removing a node only affects its immediate neighbors, not the whole cluster. Partitioning splits the key space into shards, each owned by a small replica set, balancing load and limiting blast radius. Replication stores copies of each partition on multiple nodes for durability and availability. Quorum mechanics define read and write replica counts. If n is the total replicas, w the write quorum, and r the read quorum, then w plus r greater than n gives strong consistency, while smaller values trade consistency for latency and availability. The gossip protocol propagates membership and failure information across the cluster in a scalable, eventually consistent way. Vector clocks or version vectors track causality for conflict resolution. Merkle trees identify divergent data between replicas for efficient anti-entropy repair. Storage engines use log-structured merge trees or skip lists for fast writes and sorted reads, or in-memory hash tables for sub-millisecond access. The key trade-off is consistency, availability, and partition tolerance. You cannot have all three, but you can tune per operation. Now the low-level design deep dive. The request path starts at the client SDK, which maintains a local cache of the partition map and routes directly to the coordinator when possible. The coordinator applies a hash function to the key, finds the responsible replica set, and forwards the request. For a write, it appends to a write-ahead log on the primary, applies the mutation to the in-memory memtable, and replicates synchronously or asynchronously to secondaries based on the configured write quorum. Once the quorum is satisfied, It acknowledges the client. A background compaction process flushes memtables to sorted string tables on disk and merges older files to reclaim space and remove expired keys. The read path checks the memtable first, then block cache, then the relevant sorted string tables, returning the latest version. For read repair, if the coordinator detects divergent values, it returns the latest to the client and writes the corrected value back to stale replicas. Metadata and topology changes are managed by a consensus protocol to avoid split-brain scenarios. Partition rebalancing happens incrementally, moving only the affected key ranges, with minimal impact on latency. Key takeaways for your interview. First, a key-value store is not just a hash table on a network. It is a distributed systems problem involving partitioning, replication, consistency, and failure handling. Second, always explain consistent hashing early because it is the foundation for horizontal scaling and elastic rebalancing. Third, be precise about quorum math. N, W, and R, and what happens when W plus R is greater than, equal to, or less than N. Fourth, do not ignore the storage engine. Even if you only mention LSM trees, memtables, and SSTables, it shows you understand the disk versus memory trade-off. Fifth, the trade-off between consistency and availability is real, and you should discuss how to tune it per operation rather than pretending the system is all things to all people. Sixth, mention failure detection, gossip, and anti-entropy because they separate a toy implementation from a production system. If you can walk through this system with these points, you will signal strong senior-level design thinking. That's it for the key value store. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the key value store. We covered the full picture, from consistent hashing and partitioning through replication, quorum mechanics, gossip, storage engines, and the low-level design of the request and storage paths. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.